Last time I promise I will come with the explanation of how the circuit for the power supply design works. So today I'm going to explain briefly how the circuit works. So let me share my screen. So here is the LTS spice. So now, so this is the circuit. So I have like two circuits. This is the first stage of the circuit. So here I have 10 volt DC voltage, and we want to convert this 10 volt DC to 120 volt AC. So here we have, this is a step up transformer, and we are using full wave configuration for the inverter design. So here we have four MOSFETs. The MOSFET here I'm using IRF H5302D. So these all four are same, and these all are in full wave configuration. So basically M1 and M4 has same pulse to control, to drive the gate of this MOSFET. We are using same pulse here, and M3 and M2 we are using same pulse. So for example, when this MOSFET M1 and M4 are turned on at the same time, M3 and M2, they are going to turn off. So this is main the theorem. Here I'm using transient response simulation, and it has like a stop time is 100 millisecond, time to start saving data is 90 millisecond, and maximum time step I'm using 1 millisecond. And yeah, we can also do like a stop simulation if a steady state is detected. For here, I'm not using this one, but we can also use, we can check over here. So let me simulate this circuit. So now I'm checking here, this is 10 volt DC voltage. And here we can check the pulse. So the pulse is like 10 volt. Going from here, you can see from 10 volt over here. So it's going 0 to 20, back to 20 to 0. This is like turn on position. And this is, let me add the other one. And plot lane. So we are checking this voltage over here. So both are turning on at the same time. And now I'm going to check the other one. Now let's check this one. You see here, both has like 20 volt. Over here, like M3 and M1, it has like 20, 0 to 20. And let's check over here. Now I'm going to add another plot. So by checking here, we have just like M4 and M3, they are in lower down for the inverter. Yeah, we can also add another plot to check the voltage over here. So here you see this is like 10 volt, 0 to 10 volt. When, for example, when this switch is turned on, this switch is turned on, the voltage is here is like 0 volt. And when this switch is turned on, this is like inverting, like this is turn off, turn on, like this. And we can also check over here. Maybe I can just add another plot. Adding another plot, you can check voltage over here. It has, and you can see over here when there are like two end, and this is turn on, the another is turn off. When this is turn on, this one is turn off. Maybe I can choose the color. Different color. That color is not too good. This color. So here you can see over here when this is turn on, another is turn off. When this is turn off, this is turn on, and likewise. Now I'm going to add another plot to differentiate this voltage. From here, we should have uh, change color. So we have over here like minus 10 to 10. Here we have minus 10 to 10. And we can also check another voltage. Plot. Now I'm checking the output of this voltage. So this voltage is like 120 voltage, like minus 120 to 20. We can put over here. Maybe we can see over here. So this voltage, this is the differential voltage for the node 4 and 5, and it has like minus 10 to 10 volt. This is a square wave, and the goal is for this project is to design a power supply of 10 volt DC to 120 volt at 60 hertz sinusoidal power supply. For diode 1, you see here we have like 120 volt. Yeah, this is a square wave, but we need to have sinusoidal. So for diode 1, now I'm going to open the another circuit, the final circuit. So I have the another circuit is over here. But yeah, here. So this is the final design. And also for here, for this circuit, we are just using the pulse. I mean, we are not generating the pulse, but here we are generating the pulse. In this final circuit, we are generating the pulse. Here we are just using the pulse from the signal generator. But here in this circuit, this so I used the OPM to generate pulse. So it is this is inverting OPM. So here we have like this going to inverting input, and this voltage is sinusoidal voltage, and this is just a regular pulse, the square wave pulse. So for the pulse setting, we can also check pulse setting. You can set pulse like here. Pulse is basically a square wave. So we are assuming the initial voltage is -10 and the turning on voltage is 10 volts. Time delay is 0 second. Rising time is 9 microsecond. Falling time 9 microsecond. And the time on is 1 microsecond. And time period is 20 microsecond. We are assuming like 20. So time period, the period is 20 microsecond, which is basically you can find from the 60 hertz, because this is going to use like 50 kilohertz. So we calculate 20 1 divided by 50 is like 0.02 and 1000 like 20 microsecond. Yes, that's why like because because for this one like this has like 20 microsecond. This is the time period. So the frequency is 50 kilohertz. So this circuit is same. It's exactly same as so this circuit. This circuit is same as this circuit. Only difference is over here is we are added. So we added the OPM to generate pulse, square wave pulse by comparing two signal, sinusoidal and a square, the pulse. So here, and also to convert a square wave, 120 volt square wave to sinusoidal at 60 hertz, I used cascade of two RC filters to convert a square wave to sinusoidal. So here is cascade of two, like one is over here, another over here, and there is also one. So basically, yeah, cascade of three filter, yeah. This is also 10. So cascade of three filters. And this signal is going to non-inverting terminal of op-amp, which is we are supplying over here sinusoidal. We are comparing the pulse with sinusoidal voltage to get the output. And here we have this output is going to drive the each MOSFET, but it has a different configuration over here. For example, you can see over here, it has the plus is grounded. The plus is like 10 volt. So VDD, let me see. So this is VDD, and that is over here. So the pulse is going over here, and this is the VDD. I'm assuming it should be over here. Yeah, VDD is 10 volt. So this is connected to 10 volt over here, and the negative terminal is connected to the output of here. Just like when this is in on mode, this is in off mode. Here, this is V controller, which is over here. This is the V controller, and this is the grounded, and the values are same. You can choose these values for the inductance. And as you know, like for the transformer, stable transformer, like voltage is directly proportional to number of turns, and also inductance is directly proportional to a square of number of turns. So you can calculate this ratio. And these values for the capacitance are calculated using the 60 hertz. 60 hertz, the critical frequency at the break, the frequency at 60 hertz, and we are just for the resistor value, we are just assuming like 10 ohm, and when you have like 10 ohm, you can calculate the value for the capacitance, and we are using same cascade of 3 filters. So let me run this circuit. So first of all, I'm going to check the DC voltage over here. We have 10 volt DC voltage. So right now you can see over here we have this one because we have clicked. We have, you see over here we have a skip initial operating point and also a start external DC supply voltage at 0 volt. For the time, it has like 1 second. The simulation time is 1 second. My computer is running slowly right now. So we got 10 volt over here, the DC voltage. Now we can also check this one. This is the pulse, the input pulse going to non-inverting, inverting input. To see this one, we can also we can start over here. So since this is 0.8 second, maybe we need to make more smaller. 9 millisecond. See? So the pulse is over here. This is the pulse. We can also compare the sinusoidal pulse over here. This is because maybe we can just I'm going to add the plot, another plot. Now we can look for this guy. Yeah, I mean, because this is I made very small. Maybe 500 milliseconds. So you can see over here, this is like this one. Okay, this one to 700 milliseconds. I want to see the sinusoidal one. Sinusoidal is going over here. It has a reference voltage like 5 volt. So it's going from 5 volt. Let me see how much. Now we are going to look over here. So this is also since we are using this filter, so here it's not totally like a square wave, but it's kind of like coming like filtering, like sinusoidal. Yeah, it has like 10 volt, just like before over here. We have like 10 volt. Right now, since we have like cascade of this filter, that's why it's it's yeah, it looks like sinusoidal. This laptop is getting hot. It's too hard. Maybe I can just decrease some time. I think. John Carson. So this is 0 to 10 volt. So this is inverted voltage. So basically this is inverted voltage, which is converted from 10 volt DC to like 10 volt. It's like since it doesn't look like exactly a square wave because of having three cascade of RC filters. But here you already so that having no filter we have like a square wave. So now I'm going to check voltage over here. So you can see over here, this is 120 volt RMS. So when you convert 120 RMS to, so this is sinusoidal. For sinusoidal, it's showing the peak to peak voltage over here. So this is peak voltage. So from 0 to 180, it's peak voltage, but over here, both voltage, the peak to peak voltage is like minus 180 volt to 180 volt. It's like peak to peak. So 120 multiply by a square root of 2, it gives like 169.71 volt, which is almost like 170 volt. We can also check over here. You can put a cursor over here. Yeah. So you can see over here it's 169.978, which is almost 170 volt. That is peak voltage, which is 120 volt RMS. So the design goal is satisfied over here. Now we can also we can let me choose for 40 millisecond. $49 millisecond. Now, so for one cycle, the frequency we can measure from, suppose from here, we have another cursor. We need to put another cursor over here. Two cursor. So another one we can put over here. And we can measure. Yeah, you can see over here. This is like 16.305385 millisecond. It should be like 60 hertz. So 1 divided by 16.3054 and multiply by 1000. So like 61. Maybe the cursor is some, we need to, the cursor in the right place. What's the 16.99? 1 divided by 16.99. Maybe we can measure from here. I think. Yeah, frequency you can see over here like 58.8, and it given like how close is this So it's about like nearby 60 hertz. Hold on, this is I channel out, I think. This is not in the right place. And this should be over here, I think. Middle. Oh, oh, I lost. Yeah, so this is like at 60 hertz, like nearby. Maybe I need to, let me go over here. Oh, maybe we can increase the time, the simulation time to see better results. Let me put 1 second and run this one to see the better result. I know my laptop, it's updating, I think, and it's getting too hot. It's too hot, I think. Now it's good. So in this circuit, we have used a lot of power electronics. Yeah, basically we have used the whole configuration for the inverter design, the full wave configuration using for MOSFETs. I've I have also done with 4 BGT transformer, BGT bipolar junction transistor. Sorry, and for diet one, maybe I'm going to show you with BGT also, because with BGT the result is not exactly like this one. It's like slightly different over there, because as you know, like MOSFET, it's more powerful and it has like more efficient, and BGT consume more current, so more power drop over there. That's why there is like some lagging over there. It's running very slowly. It's not even 50%. So you can also use other power MOSFET like ARIA, IRF, Z24. So for this configuration, maybe like to set up this configuration, like this is like mutual inductance, like L1 and L2. These are like coupling. We are assuming the coupling is perfect coupling, like 1, because this is not like practical. This is like more like simulation. So we can assume like coupling is 1. I also implanted this circuit in lab with my professor, Dr. Donald Zinger. That was really cool. Yeah, this project, it was almost 2 semester project. Yeah, I spent most of time with Dr. Zinger, and during this project, yeah, I got a lot of experience in power electronics, mainly with like PWM, pulse width modulation technique, like full wave, half wave configuration, like my inverter configuration, and different kind of MOSFET, and you can source the data for these MOSFET. And there is also diode, 4 diodes in base configuration. This is going very slow, and it's too slow. I don't know why. I mean, last time it didn't take more time like now. Last time it was maybe 2-3 minutes, I think. Less than 2 minutes, maybe 1 or 2 minutes. And last time I also used like simulation time for 5 seconds. That was like more time. Now it's done. Yeah, now we can measure exactly. So let me add one more cursor over here. Yeah, we have already. This is cursor 1. This is cursor 2. Yeah. So that you can see over here frequencies like 60 hertz, 60.09901 hertz. So this is sinusoidal. The goal is to design a sinusoidal power supply, just like in our home. Like in USA, like we have like 60 hertz, like 120 volt at 60 hertz sinusoidal voltage supply in our home. And in other country like Europe, like Asia, like India, Nepal, we have like 50 hertz over there, like 220 volt AC at 50 hertz supply voltage. In America, we have like 60 hertz. So the goal is achieved over here. Now I'm going to show you another circuit. So here, so first of all, when I started this design and research, I came with this one, this idea, but this is not, I mean, more effective like using MOSFET because there is like some power consumption over here. So let me run this circuit. Here we have like how much is 10 volt. So there is also 10 volt. Let me see. This is at 1 millisecond. Oh, this is at 1 millisecond. Simulation time is, the time is very, 100 millisecond. Or maybe we can just use the 1 second time to start data 0. That's why we need it. Here we have startup evaluation. Yeah, one thing we can do over here for this circuit. Yeah, we can just use 1 second. Yeah, we can come with same one. Let me. Why this guy is wrong? For now, I'm just deleting this. Changes. Yeah, that makes sense. So now this circuit, I'm going to run this circuit. So here we can check over here is 10 volt DC. And yeah, it has same pulse like a square wave over here. And I'm using like 2.5. Like over here, we can. Like initial voltage 0, beyond 2.5, like time delay 0. And these are like cycles. Let's check over here voltage. So here you can see over here, it's not exactly 10 volt. Cursor, we can choose the first one cursor. So it's 9.835 volt. It's not exactly 10 volt. Now we can also check voltage over here. So it has not exactly 120 volt. It has just 116.0437 volt. Yeah, because there is like some power drop over here. This is like PNP transistor. These are like, yeah, NPN transistor. Yeah, where we have a lot of circuit, we have here. So this is the final circuit, final design. I hope you guys understand what's going on over here in this circuit, like inside, to design this power supply. Yeah, thanks for watching. Bye.